Welcome, everyone. Today, we are diving deep into one of the most revolutionary architectures in artificial intelligence, transformers. You might recognize this architecture as the foundation behind ChatGPT, BERT, and most modern large language models that are transforming how we interact with technology. The transformer model has completely revolutionized natural language processing since its introduction in 2017. What makes it so special? It's built entirely on attention mechanisms, which allow models to understand context and relationships in text in ways we never thought was possible. In this representation, we'll break down exactly how transformers work, from their core components to the key mechanisms that make them so powerful. Whether you are a developer, researcher, or just curious about AI, understanding this architecture is essential for grasping how modern LLMs function. So let's get us started by exploring the foundation of the transformers, their core components. The original transformer architecture introduced in the famous attention is all you need paper, uses an encoder-decoder structure. Think of the encoder as understanding the input. It processes and encodes the input sequence into a rich representation. The decoder then generates the output based on this encoded information. This encoder-decoder approach is perfect for tasks like translation, where you need to understand input text and generate output text. However, many modern LLMs, especially GPT-style models, use only the encoder part. This is called the decoder-only architecture. Why decoder only? Because for a language modeling task like next token prediction, we only need to generate text, not translate it. This makes the model simpler and more efficient for generative tasks. Now, the real magic of transformers lies in the self-attention mechanism. This is the core innovation that separates transformers from previous architectures like RNNs and LSTMs. Self-attention allows the model to weigh different parts of the input sequence when processing each element. In simpler terms, when the model reads a word, it doesn't just look at that word in isolation. It looks at all the other words in the sequence and decides which ones are most relevant. This solves one of the biggest problems in NLP, understanding context and relationships between words that are far apart in the text. For example, in the sentence that the cat, which was sleeping on the couch, suddenly jumped up. When processing jumped, self-attention helps the model understand that cat is the subject, not couch. This mechanism is the foundation of both the encoder and decoder, and it's what enables transformers to capture long range dependencies effectively. The image on the right shows the complete transformer architecture. Notice how it has multiple encoder layers stacked on top of each other and multiple decoder layers. This stacking allows the model to learn increasingly complex representations at each layer. Next, let's dive deeper into the encoder architecture to understand exactly what happens inside. The encoder is where the input processing happens. It consists of multiple identical layers stacked on top of each other. Each encoder layer has two main components, multi-head self-attentions and a feed-forward neural network. So let's look at the code structure shown here. This is how you would implement an encoder layer in PyTorch. The first component is multi-head self-attention. As we discussed earlier, self-attention allows the model to attend to different parts of the input sequence. But what does multi-head mean? Instead of having one attention mechanism, we have multiple ones running in parallel. Each head can learn to focus on different types of relationships. For example, one head might focus on syntactic relationships, subject-verb agreements. Another on semantic relationships, words that often appear together, and so on. The output of all heads are then combined, giving the model a richer, multi-dimensional understanding of the input. This multi-head approach is crucial for capturing complex linguistic patterns. After self-attention, the output passes through a feed-forward neural network. This is a simple two-layer neural network with a ReLU activation in between. While self-attention handles the relationship between words, the feed-forward network processes each position independently. Think of it this way. Self-attention gathers information from across the sequence, while the feed-forward network transforms this information to learn more complex patterns. These two components work together. Self-attention brings in context, and the feed-forward network processes it. Notice in the code, in forward function, we have x equal x plus self-attention and x equal x plus self dot feed forward. The x plus part is a residual connection. It helps with training by allowing gradients to follow through the network more easily. The norm 1 and norm 2 are layer normalization. They stabilize the hidden state dynamics and make training faster and more stable. These architectural choices are essential for training deep transformer networks with billions of parameters. The diagram on the right shows how encoder layers are organized. Each layer receives input from the previous layer and processes it through self-attention and feed-forward, and passes the output to the next layer. This repeated processing allows the model to build increasingly sophisticated representations of the input. So now let's move to the decoder side, which has additional complexity for generating output. The decoder is responsible for generating output sequence, like the encoder. It consists of multiple identical layers. However, each decoder layer has 3 components instead of 2, making it more complex. The first component is masked multi-head self-attentions. It is similar to the encoder's self-attentions, but with one crucial difference. It's masked. Why masked? During training, the model is learning to generate text one token at a time. We don't want the model to cheat by looking at future token. It's supposed to predict. For example, when generating the word cat in a sentence, we don't want the model to see what comes after cat. The masking ensures that the model can only attend to previous tokens, not future ones. This is crucial for auto-aggressive generation and generating text one word at a time. This masking is also what makes GPT models work so well for text generation. The second component in multi-head encoder-decoder attention, also known as cross attention. This is where the encoder and decoder communicate with each other. The decoder as a cross attentions mechanism attends to the encoder's output. Why is this important? When generating output, the decoder needs to understand the input. For translation task, the decoder needs to know what it's translating from. Cross attention allows each decoder position to attend to different parts of the encoded input. This is what enables the decoder to generate relevant output based on the input. In GPT-style models, decoder only, this component is not needed because there is no encoder to attend to. The third component is the same feed-forward neural network we saw in the encoder. It processes the information from the intention mechanism to learn more complex patterns. The diagram shows how the encoder and decoder interact. Notice the cross-attention connection between them. The decoder takes its own output mask, attend to the encoder's output cross-attention, and process it. These three component structure makes the decoder more complex than the encoder, but also more powerful for generation tasks. Now that we understand encoder and decoder architecture, so let's explore the key mechanisms that make them work. Positional encoding, multi-head attentions, and feed-forward networks. Let's start with positional encoding. This is a crucial but often overlooked component. The question is, how does the model know the order of words? In a transformer, all words are processed in parallel, not sequentially like in RNNs. If you just fed the embeddings, the model wouldn't know which word comes first, second, or third. That's where positional encoding comes in. We add a special encoding to each embedding that tells the model its position in the sequence. The encoding uses sine and cosine functions of different frequencies. There are some formulas about position encoding. You can find them online. But this might look complex when you look at those formula. But the key insight is that the different position get different sine cosine values, and they are unique. The beauty of this approach is that the model can easily learn relative positions. It can understand that position 5 is 2 positions after position 3. This positional encoding is added to the input embedding before they are fed into the model. So now let's dive deeper into multi-head attention shown in these diagrams. The first diagram shows how self-attention works with query, key, and value matrices. Q stands for query, as I said, K for key, and V for value. This is inspired by information retrieval system. Think of it this way. When you search for something on Google, you type a query. Google matches it with document keys and returns document values. In transformers, each position generates a query, what it's looking for, a key, what it has to offer, and a value, its actual information. The attention score is calculated as dot product of query and key, scaled down and passed through softmax. This tells us how much to attend to each position. Then we multiply by the value to get weighted representation. Now multi-head attention means we have multiple sets of Q, K, V transformations running in parallel. Each head learns different aspects of the relationships. The second diagram, I don't know if you see it or not. I don't think so. Uh, uh, Shows how multiple heads work in parallel and then combine their outputs. This allows the model to simultaneously attend to information from different representation subspaces. For example, one head might focus on subject-verb agreement, another on non-adjective relationships, and so on. So another section is finally the feed-forward network. The formula shown uh, feed-forward neural network of x equal max of 0 x w1 and b1 multiplied by w2 plus b2. This is two-layer neural network with a ReLU activation. The first layer expands the dimensionality, often to 4 times the model dimensions, and the second layer projects it back. This nonlinear transformation helps the model learn complex patterns that linear operations can't capture. Importantly, this is applied to each position independently. The same weights are used for all positions. So these three mechanisms, positional encoding for sequence order, multi-head attention for relationships, and feed-forward network for pattern learning, work together to create the powerful transformer architecture. Now, let's discuss how these models are trained and what makes them so advantageous. For encoder-decoder models, like the original transformer, training uses a technique called teacher forcing. During training, we feed the encoder the input sequence. For the decoder, we feed it the correct previous tokens, the teacher, instead of its own predictions. This makes training much more stable and efficient. For example, if we are training a translation model to translate "I love AI" to French, we feed the decoder the correct French words sequentially. This is different from inference, where the decoder uses its own previous predictions. Teacher forcing helps the model learn faster by providing the correct context at each step. Another thing, GPT-style models, decoder only, use self-learning schedules. These models are trained on the next token prediction task. The model is trying to predict the next word, given all previous words. This is essentially what language modeling is, predicting what comes next. The training data is massive amounts of text from the internet, books, and other sources we don't know. This self-supervised approach doesn't require labeled data, which is why it is so scalable. But scalability, one of the biggest advantages of transformers is their scalability. You can scale them up to billions of parameters, as seen in GPT-3, 4, and other large models. They can handle both word level and sub-word level token efficiently. They can handle sub-word tokenizations like byte pair encoding, helps handle rare words and reduce vocabulary size. The parallel processing nature of transformers means they can be trained efficiently on modern hardware like GPUs and TPUs. This scalability is what enabled the rise of LLMs. We can keep adding more parameters and more training data, and the models keep getting better. Another thing is about adaptability. Transformers are incredibly adaptable to different modalities. While they were originally designed for text, the same architecture works for images and vision transformers, audio, and even multimodal tasks. For text processing, This is where they shine. NLP tasks like translations, summarization, question answering, and more. For image understanding, vision transformers treat image patches like tokens and apply them the same attention mechanism to them. For audio applications, audio transformers can handle speech recognition, music generation, and other audio tasks. This universality makes the transformers architecture truly groundbreaking. You know, something like a miracle in technology. Before transformers, RNN and LSTMs struggled with line sequence because the process takes sequentially. Transformers can capture dependency between words that are far apart in a text. This is crucial for understanding line documents, maintaining coherence in line conversations, and more. Unlike RNNs, which process sequentially, transformer process all tokens in parallel. This makes training much faster and more efficient on modern hardware. It also enables efficient batching and optimizations. But transformers consistently outperform previous architectures on virtually all NLP benchmarks, from language understanding g- to generation. They have set new standards. Every major LLM today, GPT, BERT, Claude, Llama, and more, is based on the transformer architecture. This architecture has become the foundation for modern AI language capabilities. The transformer's ability to scale its parallel nature and its attention-based approach to understanding context uh, have made it the cornerstone of modern NLP. Whether you are building a chatbot, a translation system, or a text generator, understanding this architecture is essential. So, thank you for joining me in exploring the transformer architecture. I hope this presentation has given you a solid foundation to understand the incredible behind today's AI language models. See you.